Okay, good afternoon. Welcome back to our class, CE 530. What I'd like to do today is pick up a little bit from where we went off with the introduction. I'd like to start talking about cement production. As we talked about last time, there are a few main points that we wanted to remember, a few main points we wanted to review. What is one of the topics that somebody picked up from last class? Anything strike you, Mohammed? Concrete is a composite. All right. So we know that concrete is a composite material, and we're typically going to be gluing rocks together. All right, we talked a little bit about some of the volume proportions and some of the weight proportions. All right, we noticed that water was going to be one of the trickier materials that we're going to have inside of our concrete because of its specific gravity compared to everything else. All right, so a minor change in the weight of water can be a major change in the volume, which will have a significant impact on the overall properties of the concrete. All right, today what we want to do is we want to pick up and we want to start talking a little bit about the production of cement. And what I'd like to do in the rest of the lectures, I will actually try to start off with an outline like you see on your first slide. And what I'll be doing is I'll sort of work our way through that outline. And then at the end, I'll try to give you summary points for each one of those topics. So the first thing we're actually going to cover today is we're going to talk a little bit about the history because I think it's important that we know where we're coming from. We'll talk a little bit about the production of cements. And as I mentioned last class, there is an entire course that's taught on how cement is produced. It's the production and chemistry of cement. It's a 15-week extravaganza if you're interested in it. All right, but what I will point out is we are going to do the 50-minute version of that today. We're going to hit the high points, and then we're going to be ready to move on to start talking about the properties of the cement and the concrete. We'll talk a little bit about the raw materials, talk a little bit about heating and cooling, some of the manufacturing process, some of the constraints that people have when they start manufacturing cement. We'll talk a little bit about composition, and we'll talk about some of the items that you may see out in the field, the mill reports and things like that. All right, so we're going to go through the tall and the short of cement production, and we're going to use our polar bears to sort of help us as we go through. All right, so we'll just dive right in to get started. All right, and we'll start talking about the historical perspective of cements. All right, as we mentioned last class, really what we're trying to do with our cement and water is we're trying to form a glue. All right, we're trying to come up with a glue in this composite that's going to glue the coarse aggregates together. Now, we could use a lot of different types of glue. All right, and here we see two different types of glue that are being listed. We see a white Elmer's glue, all right, that is actually going to harden up and do the exact same thing. In this particular case, Elmer's glue hardens up by losing water. All right, but that's not what we see in Portland cement systems, so they're going to be a little bit different. Or we could use super glue. We could use a glue gun. All right, and here you can see some of the finer artistic structures that have been created by the world's best 4-year-olds or 5-year-olds, all right, gluing rocks together. But this is essentially what we're trying to do. The big difference between what we're doing, all right, and using these other glues is mainly the cost. All right, we're looking for a very economical glue that's going to hold these aggregates together. All right, so unfortunately the other glues, the Crazy Glue or Elmer's glue, are going to be incredibly expensive compared to what we can get when we mix water and cement together to form a binder. Right. Now, this is not something that is terribly new. It's been around for thousands of years. All right, if you go back, you'll see early cements. Pyramids in Giza will have lime and burned gypsum put together with water. You will see the Romans understood quite a bit about making binder-type materials, all right, that could be mixed with water. They would actually add in some volcanic ash that would actually give it some very fine properties. But unfortunately, the art of making cement, all right, and the art of making concrete this way was really lost with the fall of the Roman Empire. All right, it's taken us a little while to get back to understanding exactly how cements and concretes are made. All right, one of the most pivotal things that people point out in the process of manufacturing cements and concretes is something called Smeaton's Lighthouse. And Smeaton is a guy that you will see, he comes up both on the cement and concrete side, but also on the steel production side, British engineer. And the basic problem was that they were constantly replacing this lighthouse at Eddystone. So Smeaton really started to look into ways that you could actually combine different materials together to make them more resistant to the weather. And Smeaton sort of stumbled or did some experimental testing and stumbled onto a formulation that enabled that lighthouse to be there for about 130 years, which was much, much better than any of the other materials that had been there before. Right? That leads us into really what I would call the sort of the modern age of cements, and really most people will credit the invention of Portland cement to Joseph Aspend. This is one of those things that's sort of interesting. It's kind of like Columbus discovering America. All right, Columbus discovered America, and somebody helped him park the boat when he got here. All right, so he's inventing a material that people had been using, and the real reason that he's sort of listed as the inventor is because he's one of the first people to really patent what he's doing and really start promoting this material. So in 1824, he took out a patent for something that he called Portland cement, and the real reason that he used the word Portland was he was trying to make this imitation man-made rock look like a valuable stone that was imported from the Isle of Portland. All right, so it's very much like what you see today. You see Lowe's or Home Depot, all right, selling some sort of a man-made material and trying to say that it's almost marble or it's near marble or it's faux marble. All right, he was saying that this is almost Portland rock. All right, and that's why we typically are going to refer to it as Portland cement. Now, Aspend was a bricklayer. All right, it was in Leeds, England. All right, having been and lived in Leeds for about 6 months, I can tell you that it is a cold, rainy, industrial city. All right, and Aspend was there, and he was producing these cement powders, and he was really looking for a great market where he could sell them. His product was much more expensive than what was on the market, and really the main advantage that he had with his new Portland cement was that it was resistant to water. And when they were tunneling in London, they were tunneling around the Thames River and under the Thames River, having a cement that didn't degrade when it came in contact with water was incredibly important. So he started to sell this new high-performance cement, this Portland cement, right, to really try to improve the overall properties, and it was a much more expensive material. Right. In the U.S., the process is going to be a little bit different. This is sort of an interesting little side note. One of the most important people in sort of the U.S. side of cement manufacture is a person called David Saylor. And Saylor was born in the Philadelphia area, right around in Pennsylvania, in a place called Buttstown. They sold the family store. He moved into Allentown in the 1860s. He purchased a farm and then started farming the rocks that were there. All right, in the Allentown, around the Allentown area, the Lehigh Valley, you'll notice that there are quite a few cement plants, and one of the reasons is because there are a lot of materials there where cement can be manufactured. He started something called the Copley Cement Company. Discovered, again, is one of those interesting words. He was taking quite a bit of information that was coming from other people, but developed a process where he could make Portland cement in the U.S. Right? The other cement that had been used in the U.S. was sort of a natural cement that was mined almost directly out of the ground and used. And he developed a patent and started selling the cement to the U.S. market. Now, one of the things that I think is incredibly interesting here is while Saylor is alive, all right, till 1884, the only patent for selling and manufacturing cement is by Saylor. All right? At Saylor's death in 1884, all of a sudden other companies start to figure out how to break the patent and start going into this business. So I think one of the things that's kind of intriguing about this is there's always sort of a technological side of it and there's a business side of it that go into this. You can see the kilns that Saylor, kilns that are very similar to the ones that Saylor would have been using, and there is actually a museum. If you were traveling through the southeast portion of Pennsylvania and you have no better thing to do than to kill an afternoon, the cement museum is there, and there's also a steel museum, there's a coal museum, right? Fascinating ways that you could spend your vacation. All right, one of the other things that we'll point out, one of the other big innovations that takes place, you will notice that the kilns that Saylor is using and the early kilns like Aspend are using tend to look a lot more like smokestacks or little huts or beehives. Right? They tend to go, all right, in a vertical direction. One of the other big advances that you're going to start to see is the movement from the kiln from the vertical direction to a horizontal direction. All right? And there are a couple different people who are sort of credited with this advancement. The one that I think is the most interesting is the 1876 credit that goes to Millen and Sons from South Bend, who were burning their cement type making products in a sewer pipe. Which was sort of the first time that someone was thinking of doing this horizontally. I think it's probably the first time somebody wrote it down and found it interesting enough to write down. But Ransom really starts to push the idea of the horizontal kiln because they're interested in making more and more material. They're interested in throughput. They're interested in keeping this going. Thomas Edison, you can see pictured here. Edison has quite a few patents on the cement manufacturing process and is really pushing for cement and concrete houses, and is right out of the New Jersey area where you can actually see the Edison cement works. This horizontal kiln is going to be much closer to what you're going to see today, and it's going to be in the pictures that we're describing today. So this is really another big step in the overall process. All right, so that gives us a little bit of history of where we're getting to. Now what I want to do is we're going to spend the majority of the rest of the class really voyaging into the production of cement. We're going to talk about the raw materials. We're going to talk about some of the limitations. We're going to talk about some of the key issues. And we're really going to start to really try to dig through this and try to get the most out of what we can. There are some simple compounds or major compounds that we need to use to manufacture cement, and there are some easy ways that you can remember this. One of the easiest ways is to remember the glorious picture of the Mona Lisa here. All right, and Lisa is a great way that you can remember this because we are going to need a source of lime or calcium. We're going to need a source of iron. We're going to need a source of silica, and we're going to need a source of alumina. All right, so the lime or the calcium is going to typically be coming from limestone or calcite, shale, marl, all right, seashells, all right, some big source of lime or calcium. All right, our iron is typically going to come from iron ore. It's going to be found in the clays that we're going to be looking at. Silica is coming from our clays or sands. All right, and the alumina will be coming into the system as well. And these are the main contributors that are going to go into the manufacture of Portland cement. In addition to these, we're typically going to add gypsum, all right, or some sort of a sulfate source. All right, but we're typically going to add that after the kiln process, and we'll talk a little bit more about that. So a simple way to remember the major compounds, all right, just remember the picture of the Mona Lisa. Okay. So our limestone, all right, this is going to be the bulk of what's going into the system. It's going to be our calcium carbonate or our calcium oxide that's coming in, and it's typically going to be what's going to determine the location of the plant. All right. One of the things that you could probably learn pretty quickly if you were asked to carry a bucket of rocks around campus is that rocks are heavy. All right? If you try to transport rocks, they are heavy, and it typically is going to cost you a lot of money to do it. So rather than transporting the rocks around, you typically want to try to process or manufacture the rocks as close as you possibly can to where they're starting. All right, so typically the source of limestone is really going to dictate the location of the plant. All right, we're also going to be looking at clay and shale. All right, and the clay and shale is going to bring in our aluminum oxide, our ferric oxide, and the alkalis. Now, there's going to be other stuff that's added into the system. Quartz or iron oxide may be used to adjust the proportions. There may be other fluxing agents that are added to really reduce the temperature of the kiln. And we'll keep coming back to this. But one of the most important things from a practical sense, all right, is to try to produce cement at a relatively low temperature. And sometimes we'll actually add impurities into the system. All right? And by adding impurities into the system, it'll lower the temperature, all right, at which the system is actually going to bake or cook. All right, we can lower the temperature that's required to process some of these different materials. You see it in many metals. You'll notice that a lot of times impurities can be added or other additives can be to reduce the temperature. And what's one of the reasons that we might want to reduce the temperature for manufacturing cement? Less energy. All right. Some of you will remember that you got yelled at for leaving the lights on at home, all right, because the energy bill would be crazy. All right. Imagine what the energy bill is going to be if you're running a cement kiln, all right, 24 hours a day, 7 days a week at 1,800 degrees Celsius. All right. It's going to be a pretty good energy bill. So really one of the key issues we want to do is we want to try to keep the energy costs low. All right. So reducing the energy is going to be a real key issue in the overall production. All right, so some of the steps that we'll actually go through, all right, the first thing that we need to do is we need to find this limestone, we need to find the shale, we need to quarry it, take it out of the earth, all right, grind it up so that it can be used, and then we need to store it and blend it and get it ready to be used in the overall production. So we're going to take the clay and the shale, we're going to take the limestone, they're going to be quarried, and they're going to be manufactured in a way that we can start using them in the production of our overall cement. All right, now, One of the things that I'd really like to point out here, all right, this is for those of you who are confused by the line in the middle of the picture, this is two pictures that I have seamlessly fused back together, so there's not a big fault running through downtown Denver. All right, this plant is located outside of Denver. All right, and what I've tried to do is I've tried to point out some of the major components of this. This is actually a Holcim plant. What you will notice is that there is an open limestone pit where they're actually quarrying the limestone. All right, you will see that I have given you a little green dot toward the center of the picture, which I've just circled. That little green dot is a 50-ton truck that is moving limestone from the quarry over to somewhere else, so it gives you a little bit of an indication of the scale of the overall production. You will see that these raw materials will then be crushed, they will be moved, and they will be put in something called a stack house, and this is about 8 football fields long, where the materials are going to be homogenized, because in addition to energy, one of the things that you're going to see that we keep coming back to is we want the materials to be as homogeneous as possible, as uniformly as mixed as possible before we start actually producing the overall material. They will then go through a conveyor belt where they are brought up to the kiln, and they will be put through the kiln process, but there will be a few checkpoints along the way where there will be an automated sampling type of a procedure that's done to make sure that we have the right chemistry and the right mix of materials going into the kiln. All right, because quality control going into the kiln is really going to be important for dictating the overall quality of the product that's coming out. All right, now I show you this picture for one real reason. I want you to get an idea that this is not a tiny operation. All right, we're talking about manufacturing a large amount of cement. In order to manufacture a large amount of cement, you need a large amount of the raw materials that are going to go into doing this. And I think you can get a little bit of an idea of the volumes of the types of materials that we're talking about here. Typical cement plant is going to produce about 1 million tons, 1 to 2 million tons of cement each year, right? Which typically means that they need to quarry about 2 to 4 million tons of things out of the ground each year. Right? Now, how do we get these rocks out of the ground? There are a few different ways that we can take them out. Probably the most common way is to drill a hole, pack that hole full of some sort of an explosive, and blast the aggregate to make it into a smaller overall component. There are other types of technologies that are out there. There are places where you could actually use a ripper on the back of a particular piece of equipment. For those of you who may not be familiar with a ripper, it's this thing that looks like a great big hook. All right, and that hook will go down and will sort of break up the materials, and they can be used. They will then be transported into the back of a dump truck or some sort of a conveying system. They will then be put into a crusher where we take these larger particles that have either been blasted or ripped out of the earth, and they will be crushed down to smaller components. The reason we want to crush them down to smaller components is because we want to homogenize the system. Right? The finer we're going to grind the system, the easier it is to get it sort of well mixed. The easier it is to make it more uniform. The more uniform it is, typically the easier it's going to be for us to be processing that overall material. So to go through a primary crusher, it will then typically go through a secondary crusher where it will be crushed into even smaller particles. We will get down to something that's usually below about an inch or so in diameter, so we're dealing with a relatively fine material. It will then be stored, and a lot of times these materials are going to be reblended. So they're going to be stored in a way where we're not going to just take today's production, but we're going to mix today's production with yesterday's production and the day before's production, so we get a relatively uniform material that's going through the overall system. All right. Once it goes through there, all right, again, it'll be ground up a little bit more, and we'll have a nice raw feed that can go into the kiln. All right, so we now have a material that's ready to go into the kiln. Questions on this? All right, Mike?
How many people does it take to run a plant like this, or is most of it automated now?
There's a lot of automation, so there's a lot fewer people than there used to be. But these plants, I mean, when you ask that question, it's a little bit tricky to know exactly how many people you're going to have, because you got multiple shifts. All right, because typically these plants are going to be running 7 days a week. They're going to be running 24 hours a day. All right, so you're going to have people, coming in and out, and the actual operation of the plant is typically fairly automated. But there are a lot of people who are doing different things on the plants during the course of the day. So, I mean, you're talking handfuls of people. 10 people, 12 people, those sorts of numbers.
Okay.
All right. Other questions? In case you were interested in putting a cement plant in your backyard this afternoon. All right. You might want to look into the environmental regulations before you do that, because typically it takes several years, dozen years, something like that, to get a lot of the environmental regulations worked through. Okay. All right. So we will move on then. All right, materials will be conveyed in, all right, after they've been stored. All right, and as I mentioned before, one of the real key components is quality control along the line. There are a lot of groups that are doing different ways of doing this quality control. Some of the materials will actually be x-rayed as they're moving along on the conveyor belt to make sure that the right compositions of materials are working their way into the kiln. One of the other ones that I actually found pretty interesting, I think some of you have been to the bank, where you've taken your money or your checks and you put it in that little cylinder, all right, going through the drive-through, and it gets sucked up and shot into the bank, and the teller can communicate with you even though you're not the nearest car near to the bank. There's a very similar type of technology here where they'll actually have a cylinder of material that gets sampled off of the belt. It will get sucked in through one of those vacuum systems and will magically pop into the technician's lab, and the process can start of looking at the material and doing quality control to make sure the right materials are going in. You're seeing a lot more automation going into these processes because of the cost of labor. All right. Cement kiln. All right, now that we have the raw material, all right, again, remember we want to make materials that are relatively small. What I've talked about up to this point is what's typically referred to as the dry process. I will come back a little bit later and talk about a wet process. Obviously, the difference between the dry process and the wet process is the additional water. All right, so the dry process doesn't have that water. The wet process will typically take this meal or the raw materials and will typically have it in sort of a milkshake form. All right, and that milkshake form, again, the idea of putting it through the wet process is to help it become a little bit more homogeneous. All right, but we'll talk a little bit more about the dry process, and I'll talk about some of the benefits or the differences as we go a little bit further. Now that we have the raw materials and they've moved through the overall process, they've come into the kiln, we want to start to take them and we want to start to put them into the kiln, which essentially means that we are going to start to apply heat. All right, and you can see heat is carefully shown here in the graphics by the fact that we are going into a reddish color. We're going to be heating up these materials. All right, so the idea is these materials are going to be dropped into a cement kiln. All right, so the raw feed is going to come into the cement kiln. The cement kiln is basically like an overgrown washing machine cylinder, a very long washing machine. All right, where it's going to be spinning. It's going to be spinning relatively slowly. All right, we're talking 1 to 2 revolutions a minute. All right, we're typically talking something that could be on the order of, let's say, 100 feet long for a good rough number, 8 to 10 feet in diameter for a good rough number, although these will vary quite a bit. The raw material will enter the one end of the kiln, and you will notice that the kiln is slightly tipped. All right, the material will sort of matriculate down throughout the kiln, and it will work its way toward the flame. And you will notice that I've drawn this lovely flame. All right, this is the source of where the main heat is coming into the kiln. As the material moves along the process of the kiln, it will heat up and will start undergoing the reactions that we're talking about in this particular system. While the material is moving down, we are also getting rid of a lot of the exhaust gases. All right, we're getting rid of a lot of the water and the water vapor that's coming out. We're getting rid of a lot of the CO2 that's coming out. So you can see we've drawn an arrow here where the exhaust gases are going to be coming out of the system, and a lot of times we're going to be recapturing those either due to their environmental impact, or we're going to be recapturing them because we want to try to reutilize some of the heat that's in them. As the system is going to be moving down, we're actually going to get to a point where we're going to form a eutectic melt. All right, so we're actually going to get a liquid component in the system. Now, one of the things that I will point out is that the entire system is not going to, it's not like the entire system is going to become a liquid, but we're going to melt or get a eutectic melt of about 20% of the overall system. After we pass the flame, after we've undergone all the transformations that we need to undergo, the material will then typically be referred to as clinker, and it will come out the other side of the kiln, and we will begin the process of trying to cool it down before we go and manufacture cement out of it. Okay? So to give you a few ideas or a little bit of an idea of one of these particular kilns, again, this is the plant that I had mentioned that was in the Denver area. Here you can see the size of the kiln. These are not small people. These are normal sized people next to the kiln. So you can see this one, I believe, if my memory serves me right, was about 15 feet in diameter. It was a relatively short kiln. One of the things that you will notice is that there is a roof over the kiln, and it's mainly because they were worried about when it would rain. The kiln is warm. When water hits that warm kiln, it can be a little bit difficult to see what's going on. They want to make sure that they have uniform heat inside of the kiln, right? And the kiln will be lined with refractory brick. All right, so the kiln will actually be lined with bricks to keep the steel from getting too warm. All right. In addition, you will notice that there are some items along the length of the kiln. All right, these items along the length of the kiln are typically used to cool down the outside edge of the kiln. As I mentioned before, we're looking at 1 to 2 revolutions a minute. All right, on this overall system. Here you can see sort of the business end of the kiln. There's a picture from inside, so you can see that there's actually going to be heat and fire sort of applied. And then you can also see that this line that's going into it is the fuel that's going in to supply that. So you can see that there's a substantial amount of fuel that's going to go into heating this up. All right, what is clinker? All right, this is the material that's going to come out the other end of the kiln. You'll remember that if it's going up to these very high temperatures, it's going to be a relatively warm rock that's coming out of the system. Remember, at its peak temperature, we'll have about 20 to 25% of the overall system that'll be molten or liquid. The clinker will be passed through the kiln, and it will go onto a cooling grate that we'll see in a picture of in a second. The basic idea here is to try to get as much of the heat recovered from that clinker as possible, and also cool it down relatively rapidly. The clinker will be about 5 to 25 millimeters. For those of you who are not familiar with this, that's 1/4 to an inch. All right, walnut type size material. Walnuts are golf balls, and the majority of this system is going to be calcium silicates. Right? The majority of the system is going to be some sort of a calcium silicate combination. All right? It's going to be, if it's C3S, it's going to be A-Lite. If it's C2S, it's going to be B-Lite. All right? And this is going to typically make up about 75% of the overall system. All right? That's really the stuff that we're after in the overall process of manufacturing cement. All right, so what is actually happening inside of the kiln? Right, well, again, this is another conceptual illustration. All right, and one of the things that I would like you to sort of be aware of is that there are really sort of 4 main regions or 4 main types of behavior that are happening inside the kiln. So again, we've got the raw feed that's coming in. This is the ground up limestone and clay. All right, shale that's going into the system. We've got the raw feed coming in. We've got the exhaust gases that are coming back out. Right, typically going to go through a bag house, going to be expelled, going to go through a pre-calciner or some sort of a heat transfer type of device. Right, as the raw feed works its way through the kiln, the first thing that we're going to be typically giving off is water. All right, so as we start to heat up the material, it's going to give off water. The clay will then begin to decompose. All right, the region where we're giving off water is typically going to be referred to as the dehydration zone. All right, the second zone we will typically refer to as the calcination zone, all right, because the limestone is going to be primarily breaking down in this region. All right, the third region will be the clinkering zone, right, and here's where we're going to start to form the calcium silicate compounds that are really what we want. This is where we're typically going to see some of that melt forming, and we're going to see the physical and chemical changes that are taking place inside of that meal that are going to convert it from limestone and shale over into calcium silicates and the material that will eventually become clinker and Portland cement. And the final thing that we'll see is the overall cooling zone. All right, and we'd mentioned this, so after the material starts to fall out of the kiln, all right, or as it leaves the kiln, it will begin the process of cooling down. Now, you'll see that as this is happening, all right, we've plotted an idea of what some of the relative temperatures are, all right, in degrees Celsius along the bottom. All right, so you can see the feed temperature. This is the temperature inside of the aggregate or the raw material that's coming through the kiln. The top will be the gas temperature, all right, that's up in the top part of the kiln. Okay. So again, as we mentioned, the first thing that's going to be happening, water is going to be given off, and this is going to be happening in the dehydration region. All right, so that water is going to be lost. The clay is going to be changing itself a little bit. All right, dehydration zone, first region inside the kiln. Second region inside of the kiln, all right, calcination is going to start to take place, and what we're going to see is we're going to see the CO2 begin to be liberated from the system. And while that sounds wonderful, we're giving off CO2 at this point. All right, so we're basically changing the chemistry of the material by allowing CO2 to be released from the system. All right, this is something that's becoming a rapidly emerging area of concern for the cement industry, because as many of you know who are following what's happening in the news, CO2 emissions are becoming more and more scrutinized. All right, and you can see here that the idea of emitting CO2 is really sort of a fundamental part of the overall process of manufacturing cement. All right. You will see then all of a sudden we will start to get a reaction between the solids, all right, and the solids will start to stick together, all right, because typically we've got some sort of a melt that's forming between these, all right, and then we will start to melt a little bit more of the system, and while we melt a little bit more of the system, all right, we will have one form of the C2S, the calcium silicates, all right, that'll actually start reacting, all right, and start forming inside of the overall system, all right. The system will then cool down, right, and we will now have a melt with some of the calcium silicates in it. Right, so another picture to give you a little bit of a different perspective of what's happening in the kiln. Right, these are the proportions by weight. All right, the x-axis is time. All right, so this is essentially if you were to follow one little chunk of the meal as it's going through the kiln. All right, this is what it would be doing. You can see initially the proportions we've got are basically our limestone component, we've got our clay and our iron oxide, we've got our quartz, right? The blue line is tracking the temperature of that particular meal as we're going through the system, all right? And what you can start to see is what some of the phases are, all right, that as we start to go through the overall system. You can see in the preheating region or the dehydration region, we're going to be losing water. Calcining region, you can start to see that we are reducing the volume of limestone in the overall system, creating free lime. You'll see some B light going up. What you will notice is the temperature is going to stay at a relatively constant, about 800, 850 degrees, somewhere in that region. Once all of the limestone is consumed, you will start to see a rapid rise. All right, once all the CO2 is given off, all right, you will start to see a rapid rise in the temperature. All right, you're going to also start to see the liquid melt happening, and you'll see the A-light or the C3S start forming in the overall system. All right, and then you will see that the temperature will drop off. Now, on exams or anything like that, I'm not going to ask you to reproduce this in great detail, but I want you to have a basic idea of what's happening, what are the reactions, what are some of the things that are being faced as materials go through the kiln. Right, question?
When you have that constant temperature, is that like a phase shift in a thermodynamic reaction where the temperature remains constant throughout?
Yeah, essentially what's happening is the CO2 is being given off there, and you're getting more and more CO2 given off until it's all taking place. Yeah. So it's exactly the same thing you would see on a normal phase diagram or something like that. Other questions? Okay. Once the material has then gone through, it goes into what you can think of as an industrial version of the air hockey table. All right. Some of you have played air hockey, and you know that the puck slides around, and there's some air blowing through it to keep that puck, all right, in suspension. All right. Here, what we're doing is we're going to be blowing air over the clinker. All right. So you can see here one of these grates. You can see the air that's being blown up through the grates is going through the clinker, and essentially what you're going to be trying to do here is you're trying to do two things. All right, you're trying to cool the clinker down, all right, so that it can go out and can be stored much more quickly and be processed the rest of the way much more quickly. All right, you're also trying to use this to recover some of the heat. All right, so again, one of the main things that people are trying to do is they're trying to find ways to conserve the energy, all right, in manufacturing. They are going to try to conserve some of this heat, and they are going to actually reuse this heat. All right, so as the air passes over the warm clinker, or let's just get down to it, it's hot clinker, all right, as it's coming out of the system, it's going to heat up the air, all right, and you can actually use some of that heat, all right, in the process again, all right, and you can actually save some of that energy, and we'll talk a little bit more about that. All right, here's a picture of it. It's beautiful. You can tell exactly what it is since you can see through the roof. But essentially, that's essentially what's taking place. As that air is coming through, it's not going to just have heat in it. It's going to be picking up dust. It's going to be picking up alkalis. It's going to be picking up other things. And these typically need to be cleaned in something called a bag house. All right, that bag house you can think of as sort of a large shop vac. All right, large industrial shop vac where we're sort of collecting all the dust that's in the system. And dust that comes out of the cement kiln we will typically refer to as, anybody want to take a stab at it?
Cement dust.
Cement kiln dust. All right, engineers not very creative. All right, or all the cool cats and chicks will be calling it CKD. All right. So cement kiln dust, this is the material that's coming out of sort of the recollection, or it'll actually be coming out of the grinding phase. All right, the clinker will then be stored until it's ready to be further processed. Here you can see that the clinker is being stored either in silos or it's being stored in this large round type facility. Again, the main idea there is to try to get as good a distribution of the materials that are being produced at different times as possible, so you can make a material that's relatively consistent because it's homogenized between different days of production. All right, the clinker will then be combined with gypsum or some sort of a sulfate source, and it'll be put through a grinding mill. All right, and this grinding mill is sort of like a dryer. All right, but a dryer that is filled with great big steel golf balls. All right, long dryer. All right, it's going to be rotating. All right, and these golf balls, all right, will look something like this. Here you can see a guy standing inside of one of these. And the basic process that is going to be used here is as this rotates, these balls are going to be picked up. They're going to be dropped, all right, due to gravity back onto the other particles, and they are going to make clinker into smaller powder type materials. There are other places now that are starting to use sort of a rolling pin to do this, but it's the most common way that you'll see this done is through a ball mill where they'll actually be grinding the material. All right, they'll be bringing the gypsum in as well. Now, there are a few things I will point out here. This is not a terribly quiet process. All right, if you want to get sort of an idea, you could take maybe, I don't know, a dozen golf balls or so and throw them in your dryer at home, see how much noise that makes. All right, this is can be a very loud process. A lot of times that they will actually use either filters to determine when they've got enough grinding, or there'll be acoustic sensors where they can start to tell something very similar to acoustic emission, where they'll actually be telling when enough grinding has been done. Right. So to fill in our little map of what's been happening and to go through the process a little bit more, we've started out with our limestone and our clay or shale. All right, they've been quarried. They're typically going to be refined, typically ground down. They're going to be placed. We talked mainly about the idea of a kiln. All right, but what I will point out is that on many plants you will see preheaters or precalciners, and these are a way to heat up the material before it enters the kiln. So before I sort of showed everything as the reactions that are taking place inside of the kiln, but the basic idea here is we could actually heat the materials up in a preheating facility. All right, get them a little bit warm before we drop them into the kiln. And a lot of times in that preheater or precalciner, you're using the energy that came from either the waste energy that came out of the kiln, or you're using the stuff that had come off of the clinker on the cooling grates. It then goes through the kiln. We add the gypsum. We go through the finished grinding, and you then have a product that's ready to head off to distribution. Okay. Now, take a pause for a few seconds to talk a little bit more about some of the practical issues in manufactured cement. The key rule in real estate is location, location, location. Sort of the key rule when we're starting to talk about where cement plants or grinding facilities are located. Typically, if it's a plant, you want to have a large source of the calcium that we're going to need. Water source. Typically, if we're trying to move these materials around the world, one of the things that we're starting to see a lot more is we're seeing clinker manufactured in other countries, moved around the world and being ground locally. So there are a lot of places where this will be done. Also, you need to be close to where the need for that cement is going to be, where there's going to be a large market, and where the labor is going to be there to produce these materials. As I mentioned a little bit, we'll talk a little bit about the preheater and the precalciner, and I'll show you some pictures of this. Wet process versus dry process, we'll talk a little bit about some of the differences. Reusing the heat, energy, and fuel, and CKD. This is a slightly dated map, but if you get really close to the screen, you can actually read what some of the legends are. This is something that is produced usually every year by a group called Cement America. They'll have a different map of all the plants or the different types of facilities. One of the things that I will point out, the size of the dots basically tells you about the amount of production that's going on. One of the things, though, that you will notice is that these plants tend to congregate in certain regions, and I will trace a few things out for you that sort of help to help you a little bit to identify what some of these regions might be. All right, you will notice that anytime that there is water or a source of water where these materials can be moved, there will typically be either a grinding facility or a production facility. The basic idea is you can put these materials onto a boat or a barge, and they can be moved for a relatively long distance economically. So you'll see a lot of these facilities being located where materials can be barged in, and you'll see these materials moving around the world. It's not uncommon in Indiana to get a cement clinker that could have been manufactured in Thailand or so you'll see these materials really moving around the world, and it's an industry that's really much more global. Right. Another thing that I will point out here, and these again are taken from one plant in this particular case, but it's because an older wet process was being removed and being replaced with a dry process. One of the things that I've circled here is the idea in the wet process we are going to combine the materials with water to make essentially a limestone clay shale milkshake. And that will go through the overall system. Now, you can probably imagine that this is not the most energy efficient way to do it, and the reason that people have wanted to shift to the dry process is because they don't need to drive off water. All right, the first thing that we do in the process is to drive off water. If you can get away without adding water to the system that has to be driven off, all right, you can be a little bit better off. So they've started to move toward dry process, more dry processing. All right. In addition, here you can see that there's a large tower at the end of the kiln in the dry process side, and the kilns will tend to get shorter. All right, and the reason is because this tower is what I was referring to as the preheater, the pre-calciner. All right, this is where the materials are essentially being heated up before they go into the system. Right. Now, before you are curious, yes, that is my thumb. How it's in front of the screen, I have absolutely no idea. All right, when I snap this lovely picture. All right, but what I would like you to get an idea of, all right, is this is essentially, some of you have, before Bob Barker was replaced by Drew Carey, all right, you had the opportunity to watch one of the greatest game shows in the history of the world. All right, and that game show is? The Price is Right. And the best game on The Price is Right is? Plinko. Fantastic. So this is sort of industrial scale Plinko. All right, we are going to take the materials. The materials are going to essentially be moved to the top of the system. They're going to come down the system relatively slowly. As they come down the system relatively slowly, like that little Plinko chip, all right, bouncing from side to side, they are going to be heated up. All right. Preheating, pre-calcining, you're going to see the water is going to be driven off. You're going to see some of the CO2 start being driven off. And this is typically going to be some new heat being put into the system, new energy being put into the system. But the biggest thing is that they are trying to recover waste heat that's been generated by the kiln, waste heat that's going to be coming off of the clinker as it's being cooled down. All right, some of the advantages. What I've actually done is I've shown a very small graphic over here on the lower right-hand corner. What you can see is as pre-calciners and preheaters are used, typically you will end up with a smaller kiln. All right, so there's less energy going into rotating the kiln. Improved process control is typically an outcome of the shift. The bricks inside of the kiln will tend to have a little bit longer life because it's a little bit easier process to control. They'll be able to burn different types of fuels, and typically they will see a big energy savings. All right, so you will hear a lot of people talking about the fact that cement is the same today as it was in the 1930s. Not true. All right, it's being manufactured with different environmental regulations, and it's being manufactured with different energy requirements. All right, and this is going to actually change the product that's being performed, or product that's being produced. Right? Many times you will actually see alternative fuels being used inside of the kiln, you will actually see a lot of producers that are set up to use multiple sources of fuel. So they're going to shift the fuel depending upon what's available, all right, depending upon what's locally available, and depending upon the local prices, all right, because as energy prices fluctuate considerably with changes around the world, they want to be able to adapt, and they want to go into different types of energy usage. All right, a lot of times you will see different materials being burned inside the kiln because they're being burned at different temperatures, and there's actually ways that they can actually make money or get different types of credits by burning some of these materials so that they don't need to be landfilled or they don't need to be incinerated or taken somewhere else. All right, as we mentioned before, the waste dust that is generated from a Portland cement kiln is referred to as CKD. All right, this is cement kiln dust. For a long time, this material was simply landfilled, was taken out and basically dumped on the ground. It's a very, very fine powder. Now you're starting to see people wanting to try to recapture this and reuse this as much as possible. All right, so you will see people using this in things like stabilized bases. You'll see people trying to use this in asphalt. You'll see people trying to use this to manufacture bricks or blocks, different types of products. It's a material that has a reactive component. It will typically have a lot of alkalis, typically some potassium in there, but it's a material that will have some cementing properties. And a lot of times you'll see, instead of lime stabilization for soils, you'll see people trying to use something like CKD or something like that. Obviously, storage of cement is something that should be pointed out as we go through this. As we go a little bit further in the semester, you'll realize that cement powder needs to stay dry because it will undergo a reaction when it comes in contact with water. So if you're storing cement, it needs to be kept in a low relative humidity environment. Also needs to be maintained as relatively dry. One of the things that you might want to keep in mind, you want to keep this outside of, away from walls if it's being stored in a like a large storage facility, because a lot of times you can have condensation on the outer walls, and that will cause some of this to react. You'll also see something called warehouse pack. If it's stacked too high or there's too much weight put on it, it'll actually start to look like it's forming a solid material. You want to try to get away from that. We'll talk a little bit later on in the semester about hot cements, but typically you're looking at a material that's coming through. The clinker is hot. You try your best to cool it down, but it may actually be ground, especially late summer where production facilities are really trying to keep up with demand, and the cement may be actually coming out where it's a little bit warmer. Process and review you should be aware of. All right, we've gone through this, the raw materials, homogenizing the materials, all right, taking them through the preheating, taking them through the kiln, all right, moving on, adding gypsum and getting it ready for the overall material when we're done. All right, now, after it's one of the things that we want to talk a little bit about are some of the properties. All right, and we will start off next class. We'll be talking about these in a little bit greater detail. All right, but the properties are what are the ingredients of the cement, what's inside the bag, what's the chemistry of what's in the overall bag. All right, you will see that there will be lime, silica, alumina, ferric oxide. All right, same materials we started with. All right, they've undergone a little bit of a chemical change, a phase change. All right, we will have new materials. All right, and what you will see is we have the sort of the official oxide formulation over here, the sort of the conventional chemical symbols that are used, and then what you will find out is that cement chemists like to do things with shorthand. All right, and since everything has O's in it, they sort of lop off all the O's. All right, so the lime or the calcium oxide will simply become a C. All right, silica dioxide will become an S. All right, H2O will become an H. All right, so when we start to, for the rest of the semester, when we start to look at chemical equations, we'll be using the shorthand notation rather than the full-blown chemical notation. All right, if you see something with a hat on top of it, the hat means it's either carbon dioxide or our source of sulfates. All right, the main materials that we're interested in, all right, about 75% of the system is going to be C3S or C2S, our dicalcium silicate or tricalcium silicate. We will also have two other components that we'll look at, our tricalcium aluminate and our tetracalcium aluminate ferrate. All right. What I want to do is I want to jump here for a second. I want to jump to the end. All right. to go through a little bit of a summary of where we've been, so I've just jumped to the last slide. I will start off next time, and I'll talk a little bit about the mill certs when we start off. Changes in history. What you'll see is historically cement's been around for thousands of years. The type of cement that we're using today, all right, has essentially been used since about the 1820s, all right, with Aspen and the start of the patent. Limestone, our source of calcium carbonate, our shale, our clay, our oxides are going to be the raw materials that go into the process. We're going to use the kiln to heat up the materials. All right, the main things that we're going to be doing are we're going to be driving off water. All right, CO2 is going to be lost, and we are going to start to change this aggregate over into a cement or a clinker. Right, grinding is an important part of the overall physical process. We're going to grind it down into a fine powder. Right? And then essentially the last thing that we're going to do is we're going to provide the end user with a mill certificate, and that's where we'll pick up on Friday.